we have Pedro, who's a principal data scientist at Albuquerque. And Pedro will be talking to us about generalized additive models. And over to you, Pedro.
Thank you. So first, I'd like to thank the organization for inviting me for this talk. How many of you are familiar with generalized additive models? None? OK, 1, 2. And also, I see a familiar face here. Welcome. So I'm going to talk about generalized additive models. It's something that I really have a passion on that. But I'm going to summarize. Oops. I want to summarize what is the goal here and what we should know by the end of this talk, OK? So there are a lot of pressure in these tech companies about increase the capacity to run complex models. At the same time, you have regulations that demand that those models must be explainable. They must be able to explain what it's doing, no bugs behind that. And at the same time, you see that many of the empirical results point that GAN is a winner choice compared with very complex models. So that's the summary of what I want to talk to you today. Deep and costly opaque models that these big companies are trying to generate and create are being replaced slowly by simpler, cheaper, and explainable models with comparable performance. I'm not saying that GAN is able to beat very deep neural networks, but what I can say is that GAN can get closer to that with a fraction of the cost without need to spend billions of dollars. And the empirical results also give me foundations and insights and signals that this is true, OK? So this is my goal. I'm going to motivate you in this next 10 minutes why you use GAN. First, using some news, what we can see in the internet about these very complex models, then with empirical results, and then a hands-on example on that. OK, so we are in this AI race. So everyone is aware of that. Some calls like the AI bubble, others just AI race, where all these countries are trying to get in first place. So there are many labs that are trying to spend money to find what they call a superintelligence, or try to create something that can solve any kind of problem, regardless the engine behind that. Some companies are hiring a lot of people to try to solve these problems. The cost of this AI or superintelligence is getting higher and higher. There are many of these companies that are requiring, for example, infrastructure for GPU and electricity and energy. You have also this dominance about the superintelligence. So the goal is who's going to get that first, right? And the intuition and the main idea behind is if I can find a model that can solve any problem, then we are good. But there's a problem. The problem is the costs. So the costs are getting higher, and then now we are seeing in the industry a shift where they spent a lot of money hiring people and investing in infrastructure. We are seeing a shift in the industry with some layoffs more recently, for example, in Amazon. Some of the costs here. So you can see that from 1 year to the other, Microsoft, Google, and Amazon, they doubled the investments in AI. And I'm not sure if we are all twice richer nowadays. So if they are investing the double of the money, where all this money is going to? It's not on my pocket. So it's going somewhere else. And this money is going to infrastructure, energy, GPU, but not people. OK, so the costs are getting higher, and we also have these regulations that are emerging. So these regulations are enforcing all these models follow a specific set of rules. For example, we want to make sure that the model can explain in plain language why we have these outcomes. And banks are not new to restrict this oversight. There is in the bank field something called the Basel Accord that specifies that when someone, for example, processes a loan application, you must be able to explain why this loan application was denied. And this is a classification model, essentially. You pass your information, then the classification model is going to score you. If your score is lower, then you don't have the loan. But you must know why it was denied to you that long. Secondly, these models must be auditable. So end to end, we need to know the data training process, the configuration, the versions, all the decisions that were made between the data transformation, the data ingestion, to the outcomes. And this might not be easy for very complex models because of the amount of layers that we have there. And that's why we call those the black box models, because you can't explain very well why these models produce a specific outcome. We also want to ensure that there is a human oversight here, where if someone needs a human help, he must be able to get that. So these 3 and 4 regulations that are recent from, 2022 to 2025, the most recent, they require all these 4 aspects. The first one is be able to explain why the outcomes. The second one, be able to explain the traceability from begin to the end. Have help from a human when needed, and going deep in the explainability. And as I mentioned, the very black box models, they are not able to provide you that. So what? So now we have something that is, companies are spending billions of dollars trying to build these super intelligent agents that are very deep with a lot of GPUs and that are completely autonomous. And when we talk about this super intelligence, it can be just a single system or a network system or many specialized agents working together. But still, it's a huge infrastructure that tries to solve any problem. So regardless the structure that you decide for this superintelligence, if it is just a single system, a network system, or multiple agents acting independently, those models require billions or trillions of parameters. And the interpretability here is impossible. Plus, you have a high training and prediction costs and infrastructure costs. So the question is, how can we solve this problem with a lower cost solution that achieves a comparable performance while remaining explainable? So that's the challenge. These companies are spending billions of dollars expecting to solve all the types of problems. And as you can see, as I'm going to show you, those very complex models, they are not able to solve specific types of problems, and simple problems can have a comparable performance or even beat these very complex models. And GAN can be the solution for that. What are my evidence? So the first evidence is this paper that they compare 6 winners in the Kaggle system or Kaggle web page, and they found that over these 6 winners, all in the time series field, they all use a kind of generalized additive model. They call boost machine, but all these boost machines, they are a special case of generalized additive models. We have also this other paper that investigated 16 winners, and again, for problems with respect to forecasting, classification, regression, causality, and prediction, and all winners use GAN. This other paper, which is very recent, they tried 8,000, that one, the blue one. They tried 8,000 models to evaluate problems in regression and classification, and they found that GAN is again the winner. So for tabular data, most of the winners use a type of boosting machines where GAN is a type of explainable boosting machine. So GAN can be seen as a boost machine, but even more, it can be seen as explainable boosting machine. So I'm going to show you how can we interpret the parameters in a GAN model and what is a GAN model. And finally, the last paper here, which says that GAN is the predictive modeling silver bullet. Okay, so my first, we have the academia theoretical evidence, but we also have industry evidence that GAN can beat these very complex models. So there is a model, I'm going to talk about this model deeper in the next slides, called lag lemma. And this lag lemma, he was trained in 2.45 million parameters using 7,000 univariate time series, 100 trial hyperparameter search, and then it came this small company here called Nixra, compare this huge model that has several layers, millions of parameters, was trained under thousands of different time series, and they showed that a simple, naive GAN can beat this model, being 1,000 faster and 42% more accurate. So this paper here, the lag lemma paper, was written by 18 people from several companies, Meta, ServiceNow, the old Element AI, to build this huge model. And by using GAN, a naive GAN, where you have a seasonal component, a trend component, they were able to beat this model, making that 1,000 times faster and 40% more accurate. So in summary, the strong performance without the bloat. So on many real world tabular problems, they can be solved using these GAMs or these boosting machines. And they can beat these very complex models. Also, they are cost effective. So you don't need the amount of GPUs required for these very deep neural networks with convolutional transformers and so on. GAM is also good because it helps us with the explainability. So if you remember, what we face in the industry right now is an increase in the costs from billions of dollars, the spending energy that is also huge, there is a demand for GPUs that are getting harder and harder to get that. But you can come with a simple model that can overcome all these issues with a fraction of the cost, keeping the interpretability, following the compliance and the AI regulation, and you can run in your own machine. No need to huge servers to do that. And even when a generalized additive model, they don't win, they are close to. Even for the case where these very complex and deep models win, GAN is about 5 to 10% far from the best score, which in some cases makes sense for the cost benefit, right? So in some cases, you prefer to run a GAN that is 5% less accurate than a very deep or a black box model, and then you're fine with that because you're not paying thousands of dollars doing the training. You're just using your own computer to do that. So GAN can beat these very complex models at a fraction of the cost, and even when they don't, they deliver near state-of-art accuracy models between these first-class agents that you see documented in the literature. Make sense? So I hope I motivated you why I decided to talk about GAN, because I believe GAN is one of the best choices for you have right now to solve tabular problems. And now I want to share with you what are GAMs. So if you know what is a linear regression, so you know about 80% of what is a GAN, because GAN looks like a linear regression. So remember, we have these 4 regulations here. We have the NIST AI RMF 1.0 that says that AI models must be explainable and interpretable. So if you are running models that you can explain and you can interpret, probably in the future you're going to have problem, because you need to have these regulations and validations in the future for your company. US blueprint for an AI build for right says that they must have explanation. People must know why the outcome. If I ask for a landing or if I have an email that was blocked because it looks like a spam, I must know and I must be aware of why the model decided to flag that as a possible spam. And these 2 here also summarizing the transparency and explainability that is required to manage these AI models. So let's refresh here what is a linear regression. So in a linear regression, you have an outcome. It can be for a classification, can be a regression, Y can have any distribution that you want, but my goal is have a predictor or explain why Y is there. And I have a set of covariates Xi. So alpha I, or alpha 1, alpha 2 to alpha p, can be seen as explainable variability. So this entire box here is how much I can explain y. So you can see that alpha 1 is lower than alpha 2. So the importance of alpha 1 on top of y is less than the importance of alpha 2 on top of y. So pretty easy to explain. If someone asks why my loan was denied, I can say, okay, your alpha 2 flagged there more, and that's why your classification was set as default, for example, or don't send the land or approve the money. And what is a GAN? GAN is an extension of that. So you still have these blocks here, alpha I and xi, but now you're going to decompose your coverts in smaller blocks. So think about I want to predict income as a function of education. If I'm using a linear regression, then you are assuming that there is only one parameter that explains income based on education. And if the parameter is 3, you say that for every year of education that you increase, you're going to increase by 3 your income. Now, when you move from the linear regression to a GAN model, you decompose your covert in smaller blocks, linear blocks, but now with what we call splines or base splines. So the idea is the same. You still have the blocks. The blocks tells you the importance of each feature. And in my example, theta 1 here is the importance of income. The theta 1 is the importance of scholarity or education on top of income. But this theta 1 here can be decomposed as smaller components, beta jk, that are nonlinear. So I can keep the explainability easily. I can say that the importance of education in the income prediction, for example, easily. I just need to figure out who are those beta here and my splines. So those are the splines. If you have X as years of education, then you just break years of education in amount of splines, say 7 splines. And then for each one of these knots here, you have an intersection of these splines. But graphically, what the model does is by summing these splines, GAN is able to capture all these non-linearities based on your data. And then you might be thinking, okay, that looks cool, but what about the overfitting? Because if you add too many splines, this function here can be so nonlinear that you overfitting in the training data set, and when you want to predict out of sample, it's not working. And I'm going to show you how you can deal with that. But that's the intuition. You sum all these splines, and by summing all these splines, any function, any differentiable function can be represented by the sum of these splines, which is very powerful. Okay, so let me show you a hands-on example. So there is something called the angle curve. And this angle curve measures how a person's spending on a specific good changes as their income changes. So imagine that now this double investment that Meta, Google, and Amazon, they are investing in AI, go to your pocket. And now your salary double. Is your amount of spending with food double as well? You're going to spend twice with food? Probably not, right? Maybe you're going to buy better food, but you won't double that. So the angle curve measures this dependence between the increase of the spending as a share of the income. And my example here is, for example, if the income increase, how much in the income you're going to spend, for example, in food or with food. And the goal is estimate a smooth and flexible relationship because it's not linear. You can't say that if your salary double, you're going to spend the double food. Probably you won't do that. So my goal is not find a function that explains the spending in food given an increase in the income, but the derivative of that. And the derivative here is super important, for example, for market applications, human resource applications, where you want to evaluate the change in your outcome every time that you change, for example, your dependent variable. And this might not be linear, which makes things a little bit more complicated. On top of that, real data, as you know, there are a lot of noise, outliers, and heteroscedasticity, and I need to know how to deal with these problems. And the solution, again, is the generalized additive model, because you can define your outcome and distribution that you want, and your coverts can be explained by this sum of splines that are differentiable, so you can compute this derivative easily. In Python, that's how it looks. So there are many functions or libraries that works with GAN. One of these libraries is PyGAN. And the way that I usually work with that is you specify an X matrix with your covariates. Then you have a Y outcome here, and the number of splines. So the number of splines are all those curves that you saw before, right? If you have too many splines, you might overfit. So you must be aware and decide how many splines you are using here, maybe by cross-validating your data. Lambda, it's going to be a penalizer. So you want to penalize too much nonlinearity to avoid overfitting. And then the PyGAN can provide you also constraints and say, okay, your outcome function might be monotonic or concave. For the angle curve, it must be concave. Because what happens? If your income is very low, then you're going to spend, for example, half of your income with food. But now if your income double or triple, you won't triple the spend with food. You might spend a little bit more, but it's not linear on that. So the goal is fit a nonlinear model that I can explain because of the regulations and everything that I told you, and also evaluate the derivative of that. So GAN can give to you not only the prediction, which is this function here, but also the derivative of this function that tells me the elasticity for every amount of increase in my household income, how I'm going to spend my share with food. And as you can see, if the income is low, most of your income goes to food. You must spend half of your income buying food. But as your income increases, this is not linear. It decreases, this share, until you have something like an asymptote here. Can you see some issues with this plot? So PyGAN is cool because you can find the splines, but can deal very well with the heteroscedasticity. You see that the confidence interval here of the credible interval that is provided by PyGAN doesn't include my points. So that's why usually I combine PyGAN with another tool, which is Pyro. So Pyro here is a library that runs Bayesian models or Bayesian inference on top of GAN. So we can define a Bayesian structure for that. For example, after my talk, Bill Engels is going to talk a little bit about PyMC, and I hope he can give you guys an introduction of Bayesian inference as well. But I'm going to anticipate that a little bit. So remember that this is GAN. We have our GAN model as alpha I, the linear explanation of xi, and theta jk is the contribution of every spline. But since you have the contribution of every spline, you can also have the contribution of the full block for a specific feature. So every block here is the amount of explainability or importance of that feature to explain why. While for theta 1, you have smaller blocks here that decompose the importance of these features to explain why. Interpretability again. When you move from standard PyGAN to Pyro, now you define a distribution or a probability distribution for every one of these thetas. So maybe theta 1, it's more flat. You have a lot of variability in theta 1. And this might happen, for example, if you have a lot of outliers at the end of the distribution. Or maybe center or average values or centered values, they have less variability. So that's why for theta j, for example, the distribution has lower variability. So in Pyro, you specify the distribution of every one of these thetas to make the model able to deal with outliers, noise, and even heteroscedasticity. So this is the implementation in Pyro. It looks scary, but it's not. So the first term here is the splines. Remember, splines are those curves that help me to fit a nonlinear model. Then I find my splines here, say 10 splines. I get my design matrix. What is a design matrix? Just a huge table with your X, but now each one of your covariates are decomposed in small splines or smaller blocks. Then I have two matrices here. One matrix that I'm going to model the location. For example, this matrix B here, it's a matrix with my splines, and it's going to help me to predict the average food share given income. While the second matrix here, the beta sigma, it's going to help me to fit the heteroscedastic process. So when I send that to Python and I start control, for example, the nonlinearity or the wigglings of this function, I can penalize very nonlinear models and let, for example, everything be a flat line, or I can let the model fit in the best way as possible. Of course, always validating that or cross-validating. There are other parameters that I need to specify. For example, beta 0 here is an intercept. So I go to my Pedro and say, hey, beta 0 now follows a distribution, a normal distribution, with mean 0 and the standard deviation 5. And we call that these hyperparameters for my prior. Then you have eta here that are, for example, my regression effects. You have the heteroscedastic effects. So in this model, you have effects for the location. You have effects for the volatility or the variance. You have an intercept for the variance and two penalizers, lambda mu and lambda sigma. So lambda mu and lambda sigma, they're going to help me to control that. They're going to help me to control the wiggleness, to make sure that both my location and the scale models, they are not so nonlinear. So I can avoid overfitting. And after run that, so let's move a little bit here. Okay, so this is how you call the model. So you just ask the minimization of the loss function, which is going to be related with the posterior here. You pass all the matrices that you want, the amount of steps, and boom. Now I have my posterior for the location, and I'm able to fit very well the heteroscedasticity. So again, this is a very useful example, for example, for marketing, because they want to know for groups of income, what's going to be the propensity of these people change or invest their money buying books or buying food or any other good that they want. And finally, applications and real case studies of that. So if you scan that, you're going to see a case study for Stitch Fix. So it's a company that the goal is trying to find personal styling. So you go to the website, and then you want to know, okay, I'm going to wear a T-shirt or a tie, which kind of style I want to follow. And then the problem that they have at the moment was, how can I send emails for specific customers, maximize the chance of them become a customer or buy a product. So this is a classification problem. So the problem was they want to improve the direct mail performance by predicting which clients will accept an offer and target them first. The challenge is that they have a huge data set with noise data with 6-8 mixed credit demographic variables. Some of these black box models and complex models, they did the job, but they learned that GAM was able to beat these very complex models and costly models. So this is a real industry example where GAN beat all these very complex models. Here's the result. So you can see that GAN was able to find a higher area under the rock curve. It takes a little bit time to train, but that's fine, and the score time was lower. Compared with random forest, compared with SVM, linear logit, and KNN, GAN beat all these models. But the problem that I was more impressed was for the Nixla. So if you scan that, you can see the Nixla problem, where they compare the lag llama model. There was a huge model with millions of parameters, training in a very, very large scale, spend a lot of money on that, and the simple seasonal naive GAM beat this model. So in 105,000 time series for this M1, M3, M4, and tourism competition, they found 42% more accuracy and 1,000 times faster than the lag llama, with essentially paying nothing for that, running in a local computer. So this is the result. You can see here the comparison of time. So where the seasonal naive was like 2.9, the lag llama was like 5,000. So it was pretty huge. And how they did that? So they combine GAM in a trend structure. So they have a time series. They had one model, one GAN model for the trend, one GAN model for the seasonality, and one GAN model for the volatility of the process. And the kind of spline that people usually use for time series is the cyclic cube spline. That looks like this, okay? So what are the limitations? As I mentioned at the beginning of my talk, I'm talking only about tabular data. So there are a lot of research nowadays for generative AI, computer vision. So right now, GAMs can't deal with computer vision problems, for example, but there are research on that ongoing. Same idea for text, image, graph, and LLM is still these deep encoders and deep neural networks, they are required, but there are problems, research on using GAMs on that too. And the last limitation for GAM is extrapolation. So if you don't select very well your splines, then to extrapolate can be a problem. GAM works well if you want to predict inside the range of the data. But outside the range, it's not something that is easy unless you have, for example, a time series model like that, where you can decompose all the components, and then you extrapolate the components independently, and then join everything together. So that's it. I know that's a lot of information. Open to questions if you have some.
Yeah, so I have a bit of a niche question here. One of the problems that I think a lot of people don't understand is LLM's incapability to solve partially observable Markov decision processes. And I know part of like solving, getting them to get to that portion is actually incorporating a more probabilistic approach into LLMs and using your GAMs, PyMC kind of blend here, right? And with Pyro, I was just curious if that maybe has any stems to solving those problems in the future.
Yeah, exactly. This is I think the golden search nowadays. So the companies are seeing that they can't keep spending money because the evolution of these models are getting slower and slower, and it's not by buying GPUs and having huge data centers they're going to be able to attack this problem. So there is an ongoing research exactly in this direction that you said, where you have this Markov chain of probabilities models, but instead of one huge model that has billions of parameters, you have specialized agents that can be seen as gamma models because they can adjust the nonlinearity based on the splines. There are computational challenges here because optimize that might be difficult. So that's why I see some people going to this Bayesian inference field, because instead of try to maximize, optimize a very complex function, they generate values from the posterior. So specify the priors, generate values for the posterior, and get closures. So the one that solves that, it's going to be a millionaire because that's where everyone is looking for. Like LLM is the hype nowadays, but it's costly. It costs money and it's slow. So how can you solve that with a fraction of the cost? DeepSeek tried to do something like that. I don't know exactly what they did, but is in that direction. Try to create models that can run in simple computers with a fraction of the cost. That's the challenge of we are facing nowadays.
Just a follow-up to that, that's interesting. So I know that there's a lot of pressure for the general model or the super AI or whatever. I apologize for not having the right term for that, but no, I'm fine. Anyway, so and you said at the beginning that there's a tension. Is there a tension in because this what's the term I'm looking for here? AGI. So this pressure toward AGI seems counterintuitive to what you're saying, that there's this idea like, well, if we parse it out into something that's similar to multiple.
Exactly,
yeah.
exactly. And that's what I'm seeing in the industry, because if you start researching for small companies, they don't have resource and budget to run what Meta and Amazon and Google does. But they are able to find good results. Maybe not beating these LLMs, but 5–10% lower might be fine compared to spend billions of dollars, right?
So big companies are going to keep going this way, you think, and then
I'm seeing shifting. I don't know, I'm not insider, but I'm seeing a shift, for example, from Meta and Amazon to decrease this pressure because they are seeing that the investments are not paying off that. So they're seeing that they are keep investing, but the scale and the capacity of those models are not getting exponential as they are doing with the amount of investment. So what now? They are going to give up? No, they are shifting to smaller agents that are able to adjust themselves faster, easily, with a fraction of the cost. And my suggestions are GAN. Why they don't like GAN? Because of the nonlinearity, it's difficult to optimize that. So a deep neural network is a bunch of simple linear models that are easily to optimize. GANs are not so easy. So my suggestion would be going this Pyro or Bayesian framework, because we might solve that there.
I can also enunciate that's easier. So with spline models or kernel models, I understand it in the continuous sense. When you talked about, you mentioned categorical features. How does that look?
Okay, that's a good question.
Literally, the spline is useful for smoothness between continuous on a continuous domain. I have to. Oh, right, because there's people
Yeah,
online,
it's
aren't
recording.
there? Okay, so the question was, splines, kernels, other basis function approaches make sense when the domain is continuous because they provide smoothness on a continuous domain. When you have a categorical variable, does that just play into the linear term, or is there some sort of nonlinearity in that as well?
Yeah, that's a great question. So it depends on where your qualitative or discrete data is. If it's on outcome, then you specify a discrete distribution for that, like a Poisson distribution, a geometric distribution, and you are done. If it is on the right-hand side of the equation, then two approaches. You can hot encode, and works fine, because the hot encode is going to give you the contribution of each one of these parameters overall. So I wouldn't go to a nonlinear model. I would just keep as a hot encoding. But there is also discrete kernels that you can use. So there are discrete kernels that you can replace by, instead of using splines that are continuous, as you mentioned, they are discrete in the support. I think I never saw an application of that with GANs, but I know there exist discrete kernels that can be used for this purpose, where you can average the neighborhood of that. So if I have, for example, 1, 2, and 3, and then 2 is weighted based on 1 and 3 if you have, for example, ordinal data. It's like discrete but ordinal data. If it's qualitative, I think you can't avoid a hot encoding. Maybe you can map that to a continuous space. That's another strategy. For example, a factor analysis where you have your discrete data, you can map the discrete data. It's similar to the transformer. You map this discrete data to a continuous space, like in embeddings. You map that to an embeddings and then run your GAN on top of these embeddings, which is continuous by definition.
Yeah, okay. Thank you. Thank you.
Any last questions? We have 2 minutes. Okay, no questions. Oh.
This is very interesting, the explainability part. Intuitively, if you talked about the problems of overfitting. When I think about a spline, I think about, a spline overfits almost by definition.
Yes.
That is, it's almost like you're imposing an explanation.
Exactly.
Go ahead.
No, please.
So I guess I'm looking for like kind of the intuitive grasp on how you avoid introducing an explanation externally, yeah.
Yeah, that's a good question. Exactly because if you let these splines do their job, you have something that is so nonlinear that you lose the explainability. So there is a mid-ground where you can't have something that is linear, but not too linear. So in GAN, you can do that in 2 ways. There are multiple penalizers. One is like define the curvature of your function. So you say, I know, because I'm an expert in the field, that my outcome should look like a concave function. So you know that because you're an expert or you have research on this and you know that must look like a concave or a monotonic function. So that's one way you can control that. A second way is based on, what is that? Here. One more. Here, in your posterior or likelihood or loss function. In your loss function, posterior or likelihood, you have S that measures the wiggliness of your function. So it's how wiggle is your spline. And lambda is a penalizer. So you try to push and pull at the same time to make sure that you have some that you can interpret and is not non-linear. I mean, not too non-linear. So I'm a statistician, but I work mainly with economic models. So in economics, you know by definition that I want my outcome be concave or be monotone, otherwise I'm not able to explain the interpretability or the elasticity of the problem. So we define that beforehand based on the theory. And then once I know this, my model is going to fit what the theory told me that it must look like. But if you are interested in a data-driven problem, that might be hard because you don't know the structure of that. So you need to keep trying to validate and cross-validate until you find something that it's meaningful for the interpretability. The only problem is that if you have something that is too nonlinear, then this idea of blocks you might miss because some parts of the support can be a negative slope and other parts of the support can be positive. So you need to break that and explain where the slope goes down and when the slope goes up, right? Like this. I think